Swayam Prabha. Digital India. Educated India.
We'll now be looking at the problem of capillary rise in tubes and between plates. This is a historically very important problem in the field of capillarity. When one mentions capillarity and surface tension, the first problem that comes to most people's mind is the capillary rise in tubes. This is also very important problem biologically because blood transport to the further reaches of the human body, or it could be water basically reaching the furthest branches of a tall tree, or gas transport in the lungs. They all depend on capillarity and capillary phenomena. So we will be looking at this problem from three different angles. Most of you may have looked at this as a force balance in your high school, and we will be first starting off with that force balance approach. As has been the spirit of the last couple of lectures, we'll also be looking at energy minimization. I'll do this a little carefully to explain how the energy minimization occurs, because some of you may not have seen the expression of for the height, the capillary law, the law of capillary rise derived using energy minimization, and we'll also physically interpret this in the form of pressure imbalance. After a discussion on capillary rise between in a rigid tube, then we will investigate the case of capillary rise between flexible plates. This obviously is flexibility of surfaces is something that occurs in a wide range of systems. For example, if you dip a paint brush into a pot of paint, then you will see that the bristles of the paintbrush would clump together. They tend to come together. And the same thing happens when if you have long hair and you wet your hair, then you'll see that a person having long hair, the wet hair tends to clump together in bundles. Now, a detailed study of elastocapillary phenomena, where elasticity of the surface of the plates and surface tension effects, a combined theory, is a detailed theory, is beyond the scope of a course. But we will do some simple scaling estimates to get an estimate for what is the height of the capillary rise in such a flexible system. So we'll begin the discussion by looking at force balance approach for a rigid tube. Let's look at what are the parameters that are there in the problem. So parameters relevant in problem, these are geometric parameters such as radius. Then we have external parameters like gravity. So this is a tube that is in gravitational field. We have the contact angle that the meniscus makes with the inner walls of the tube. Then we have various surface energies, or let's just call it a surface tension. Or if I want to be precise, we have the solid liquid. Then we have the surface energy of the solid and surface tension. And finally, we have the density rho, or you can even say density delta, the density difference. Now, if we say that the fluid has risen to a height of h, then we can expect that this height would be a function of all these parameters. But some of these parameters can be combined through the Young's law. For example, these parameters combined using Young's law, which means that the difference in the surface energies of the solid and the solid liquid to the surface tension of the liquid will give us the cosine of the Young's angle. Now, if you look at the other parameters, we have surface tension, gravity, and G. This also gives us surface tension, gravity, and G. These three parameters combined gives us the capillary length, which is gamma by rho G. And we have, this is the length scale, the capillary length. The other length scale is the radius of the tube. So if the radius of the tube is much smaller than the capillary length, then surface tension dominates and the fluid can rise to a great height. And if if the radius of the tube is comparable or much larger than the capillary length, then gravitational effects dominate and gravity tends to pull the column of the fluid inside the tube down, and therefore the height would be very low. So even without doing a detailed analysis, one can make some, let's apply our intuition to look at what will be the expression for the height of this. Now we know that the driving force for this problem is surface tension. So we can expect that the height to which the fluid rises will be proportional to surface tension. We also know that gravity is going to oppose this. When fluid rises up, gravity tends to pull it down. Therefore, gravity would be inversely proportional. The smaller the tube, the greater it would rise, because a thinner tube means surface tension basically becomes more important, and that's again what I was saying in terms of the radius versus the capillary length. A smaller tube would mean the fluid could rise higher because surface tension would dominate over gravitational forces, and therefore again we would have an inverse proportionality. So if I basically look at all these three, I can make a guess that the height to which the fluid would rise would scale with surface tension and then inversely scale with G, rho and R. If you do a detailed analysis, then we'll basically get the effect of the angle as well. And that's exactly what we're going to do now. Let's do a force balance. The idea of the force balance is we have a contact line here, and we have a surface tension gamma, and the vertical component of the surface tension force would just be gamma cosine of theta e. So surface tension force vertical component, the surface tension force, we'll call it as Fs, and this would be gamma cosine of theta e. That's the surface tension force, and we have to multiply it by the length over which it's acting. That will be a circle of 2 pi r. Now surface tension tends to pull it up, and what is opposing it is the weight of the column. This weight of the column, because of gravity, we'll just call it as Fw. This will simply be mg. And what is mass here? Mass will be density of the fluid in the column times the cross-sectional area times h. This is the mass, and we multiply it by the gravity. And if we equate these two, of course we're making an assumption that r is much smaller than h, to suggest that the finer details of the meniscus. The meniscus is actually a curved object, so I've treated it like as if it's a cylindrical column, but the upper surface is not perfectly flat, but I'm ignoring the little change in the mass because of that upper surface. This is perfectly valid when r becomes much smaller than h, and the errors that you make are very small. And therefore, if we equate these two, I'm sorry about that. Equating the forces will simply give us Fs is Fw, or rho g h square, rho g r square pi h times g will be gamma times cos theta e times 2 pi r. A few things get cancelled out. Pi straight away cancels out. 1 r also cancels out. I wrote g twice here, sorry about that. And finally I get the height h to which the fluid rises will simply be gamma cosine of 2 gamma cosine theta e by rho g r. Now, you can clearly see that h goes inversely proportional to r. So, if you have very, very tiny capillary tubes, then if I take the liquid to be water and r to be about 100 microns, that's 0.1 mm, which is the typical size that you will see in several plants, then the height to which the fluid would rise would be around 15 centimeters. And if r basically becomes 10 microns, then this height reaches 1.5 centimeters, and this can become tinier and tinier as in several systems. In addition, the walls of this capillary tubes need not be perfectly rigid. They can also be flexible, and that can cause the capillary tube to shrink in diameter even more, and we will see the effect of elastocapillary effects a little later. So let's look at, this is the force balance, and several of you, or most of you, must be familiar with this kind of an approach. Let's look at an energy based approach. The idea of energy minimization is as follows. Let's consider two states. We have a column where this is the initial state. So we have a tube here. And let's say the length of the tube is L. And let's say that the radius of the inner surface of the tube is R. And we'll also designate the area outside as, this is the solid plate, by the way. This is the tube, by the way, cross section of the tube. And the radius outside, let's call it as A naught. And the radius, you can see this, there's a meniscus inside as well. This radius, we'll call it as AI. This I will designate as the initial state. The initial state, the energy simply would be EI would be gamma times A naught, that is the surface tension of the entire region outside, flat region outside, plus gamma times AI, right? Are there any other energies that we have to also consider? We also have to consider the inner surface area of the tube. That's basically gamma solid times 2 pi r times L. That is the inner surface area. I'm deliberately ignoring the outer surface area of the tube because it does not really contribute anyway. Well, we could still write it, but for now I will ignore it. Okay. Now, let's look at the final configuration. The final configuration is as follows. We have a tube. Now we have the outer region has not really changed much, but on the inside the fluid has risen to a height of capital H. The fluid has risen to a height of capital H. And the centroid of this region, of this column, the center of mass of this column is H by 2. Now, the area up inside still remains AI. Sorry about that. the area still remains AI, and the area outside remains A naught. Right? Now, remember that the total height that we have interested in was L, and therefore this region, where the dry region, where the part of the tube which is not where the fluid has not risen to, is L minus H. This little region above is L minus H. Right? Now let's write down the final energy state. Final state in this case, let's write down all the energies that are possible. EF. Now area outside will be gamma times A naught. Area of the meniscus inside is gamma times AI. Those things have not really changed. Now we have the part of the tube of height H is basically covered with a liquid. So we have gamma solid liquid times the surface area of the cylindrical portion of the column that I've shaded in blue. And that will be 2 pi r times H. I also have the surface area above, which is the gamma solid times 2 pi r. Now L minus H is the only one which is exposed to the air above. That's a dry portion of the solid. We also have to take into account the potential energy. The potential energy would be mg and small h, where I have mg small h, and the small h is nothing but capital H by 2. Mass we already saw here. This is density times the volume. That will be pi r square times h. Right? Now let's put everything together. We can calculate delta E, that is E final minus E initial. Let's write this down just for the sake of clarity. Now I can make some cancellation here. We'll just first write it down and then we'll do the cancellation. Gamma SL 2 pi r h plus gamma S 2 pi r into L minus h plus half rho pi r square h square into g. This will be the final energy minus the initial energy, that is gamma A naught plus gamma AI plus gamma solid 2 pi r times L. Now a few things can be straight away cancelled. The area outside does not matter. There is no change to the area of the meniscus before and after. The contribution of the solid also will cancel out. So we have gamma S times 2 pi RL. Gamma S times 2 pi RL will cancel out. And what we now have is delta E essentially becomes 2 pi R into H, that's 2 pi RH into multiplied by gamma SL minus gamma S plus half rho pi r square h square into g. This is basically what I have here, right? Now I can take a look at this relationship here. This term is involving change in surface energy and this quantity is change in gravitational potential energy. Now also notice that if you look at this relationship, I have the first term goes like E and the second term I hope I've not made an error in the, okay, the first term goes like um, h, and the second term goes like h square. Now, let's basically define a new parameter. Let's call it the impregnation parameter. Parameter I. And this parameter I is often useful when we look at problems in capillary rise in tubes, and this quantity I is gamma S minus gamma SL. This is called the impregnation parameter. What does this parameter tells us? If I is greater than 0, it means that the surface energy of the solid is greater than surface energy of the liquid solid interface, and therefore in such a case, wetting of the solid lowers the total energy of the system, right? And if this happens, fluid would rise in the tube, because the surface energy of the solid is more than surface energy of the liquid, of the solid liquid interface or the solid liquid surface. And therefore, when by the fluid penetrating into the solid or impregnating into the solid, into the tube, it is basically covering some of that energy, what was earlier gamma S times area with gamma SL times area. Therefore, the overall surface energy is reduced, and this is fluid rising is favored. The reverse is true when I is less than 0, then the fluid tends to dip into the tube rather than rise up. Now, I will not mention that, but essentially, once we have this parameter, it's a useful parameter, and it's if you're looking at capillary rise in tubes, then I is positive. I is greater than 0 for capillary rise. I'm using the word rise in its precise way, which means that the fluid is actually rising. If it was negative, then the fluid would not rise, it would fall in the tube. Okay. Now, having taken I defined as gamma S minus gamma SL, I can go back to my expression for the energy, and the energy now becomes 2 pi RH times I plus half times rho pi r square h square times g. So if you look at this expression for E, delta E, it has two parts. One part basically is negative, that is with the H term, and so for very, very small h, you would expect that the fluid would rise up, right? So the fluid would, so we are plotting delta E versus H. So for very, very small heights, then there is a tendency for the fluid to rise up because the fluid tends to lower its energy. This is negative. And then if the fluid rises any further, then there is a price that you have to pay, because the second term is which is the h square term, becomes positive. So we have, this is the linear reduction. This is the slope of minus h, and this, the second part here, this is parabolic with a slope of with h square, dependence is h square. So clearly there is a minima that you can expect. There is a special h, and to get that h, what we simply do is the stable height is obtained, stable equilibrium height is obtained by lowering the energy. By lowering or minimizing the energy. And how do we achieve this? We say the derivative of the energy change with respect to height has to be 0. That's the minima of this curve, and I simply have minus 2 pi r times I plus half rho g pi r square times 2h is equal to 0. I simply get h will be 2 times I by rho g r. And what is the expression for r that we had here? The expression for I, recall that I was gamma s minus gamma sl, which is exactly same as gamma of cosine theta e using Young's law, and therefore the final height would be 2 gamma cosine of theta e by rho g r. Now, this law is also referred to as the Jurin's law. Now, Jurin was an English physiologist in the 1700s who basically noticed carefully did experiments to determine the relationship between the height that the fluid reaches to in the tube and the inverse relationship between the height and the radius or the diameter of the tube. So if he did systematic experiments. I mean, several people even before Jurin had also done these experiments, but for various reasons, historical reasons, Jurin's name is associated with this law. Now, we will also look at one final approach, which is the pressure approach. Or simply the pressure argument. The argument for pressure is quite straightforward. We basically have a capillary tube here, and we have the fluid. This is the original height to which the reservoir is. Now let's identify a point here. Let's call this point as B. The fluid has reached the very top, and a point just below is A, and the pressure above is P naught. Okay, and recall that the angle was theta E. So if I use the pressure at A, which we'll call it as PA, this would simply be I can use the Laplace pressure jump because I have surface tension and curvature. There will be a difference in the pressure. That will be P naught minus 2 gamma cosine of theta E by R. In this case, the curvature is basically R by the curvature itself, radius of curvature, is R by cosine theta. That's the radius of curvature. Is R by cosine of theta E, and the fluid would basically rise to that. So now notice that the pressure is actually lower than the pressure above. That's the atmospheric pressure because of the meniscus shape. So it's like a suction that is experiencing, and the pressure at B now would be same as P naught, because this point P is at the same level as the level outside the capillary tube on either side of the capillary tube. Now we also have to recognize that the pressure at B is P naught, and the pressure difference between A and B is now purely hydrostatic, right? So this PA minus PB essentially would be hydrostatic, and that will be minus rho GH. The reason I wrote minus rho GH is because the pressure at B, the pressure at A is lower than the pressure at B because of just because of gravity. As you go up, the hydrostatic pressure decreases, and therefore if I substitute this expression, I have P naught minus 2 gamma cos theta E by R, that is PA, minus PB, that's P naught. This will be minus rho GH, right? And therefore I can cancel this P naught out, and what I simply have again is H goes like 2 gamma cos theta E by rho GR. We arrive exactly at the same result. So we have seen the problem of capillary rise in tubes through three different ways. We have looked at, quickly summarize it. We have looked at first a simple intuitive approach we have taken. We can make a guess, and I would encourage all students to try and do this for various problems. Before you actually try and do a detailed theory, try to think about what are the driving forces and what are the opposing forces. If equilibrium is established in a system, then forces have to be in balance. So surface tension is the driving force, therefore it has to be in the numerator, and gravitational force has to be in the denominator. So gravitational force would be a product of the density or the density difference and the acceleration due to gravity, and therefore that would be in the denominator. Then the next question would be what about geometric parameters? In this case, the geometric parameter that is relevant is the radius of the tube itself. So we've looked at capillary rise in tubes. Now what we want to do is we want to look at the problem of capillary rise in between flexible surfaces. Now let's consider a system like this. I will show an experiment in a minute. This is elasto capillary, you can say it's imbibition, or elastocapillary rise. Okay, now the idea is following. So let's consider two parallel flexible plates with a bending stiffness. Let's call it as B, and you can even we could even write it in terms of the elastic modulus and the moment of inertia. I will call it as B for now. Now we have two flexible plates that are basically dipped into a bath of fluid. And if you have two flexible plates that dip into a bath of fluid, immediately surface tension would basically start to rise up because as if they were rigid plates. But if you look at the force balance would be on the surface of the tube, that surface tension would basically pull everything towards itself, and therefore what it would do is the normal component of the force on the walls of the surface would be pulled inwards. Okay, and recall that when we've done the analysis for a droplet, a force balance approach, let's say if this was theta E, then there is a component of the force which is vertically up, that is gamma sine theta E. And I mentioned that if we zoom into that region, then locally what you see is that the solid, if it's flexible, would slightly deform, right? This deformation occurs for soft solids, and in the case of flexible plates like this, it tends to get pulled in, and this pulling in is what is responsible for clumping of hair, right? Now one has to be one has to take one important thing into account. If we look at standard surfaces like glass as a medium, then its surface tension is of the order of 250 millinewton per meter. That's the surface tension or the surface energy of the glass. But then its elastic modulus, this quantity is G, and this quantity is around 20 gigapascals. And therefore, if we calculate a quantity which is sometimes referred to as the shear elastocapillary length, this is the length scale that comes about, the length scale of deformation um, on the surface, that visible deformation that is present on the surface because of the surface forces. The surface forces can actually cause a shear on the surface and deformations on the surface, and the length scale of this deformation is basically what this quantity Ls is. This we'll call it as we'll use something else. We'll call it as Lg. This is shear elastocapillary length, and this length scale in the case of glass would be something like the surface energy to the elastic modulus, and this will come out to be around 10 picometers. In other words, the deformation just because of surface tension or surface energy will be so the deformation is so small that you will practically never observe it. So for all practical purposes, as far as only surface energies are concerned, because of surface tension, you can assume glass to be fairly rigid. Glass is not going to deform. This is also true for metals as well. If you take, let's say, copper, then the surface tension is is again comparable. It's around, instead of 250 millinewton, it's around 1.8 or 2 newton per meter. But the elastic modulus goes up even more, and therefore this length scale Lg is again around tens of picometers, right? But many biological systems, you have biological materials are often made up of soft tissues. We are also able to synthetically make surfaces or materials which are soft, which can deform, like PDMS surfaces are commonly used in engineering applications. So we can use compliant materials. There are several compliant materials that are commonly available these days that one can make. Here the G is much smaller. It typically goes from anywhere from 0.1 to around 1000 kilopascals. Now it's much larger than the 10-20 gigapascals that we were looking at, and the surface tension for such surfaces, this quantity is also anywhere between 0.01 to 0.1 newton per meter. And if we can calculate this shear elastocapillary length, this will typically range from several nanometers, around 10 nanometers, all the way up to 1 millimeter. So 1 millimeter is something that is comparable to the capillary length, and you can actually start seeing these are length scales. 1 millimeter is a length scale that can be seen often with the naked eye as well. It's certainly easy to observe experimentally. So compliant surfaces, there's an active area of research on elastocapillary effects. Elastocapillary effects is where elasticity of the surface and the deformation and capillary induced deformations of the surface become important. These days, engineers have been able to make, physicists and engineers have been able to study problems such as capillary origami, which is where if we take a droplet on a small piece of flexible surface, then the contact line forces, the forces at the contact line will tend to pull the surface and close itself into a beautiful origami shape. Now, how do we analyze this problem? The idea is basically fairly straightforward. Now let's look at the figure that I've drawn here. The idea is following. So there is a portion of the fluid of this which is dry, and there is a portion which is wet, right? And let's say the total length is approximately L. Now I'm ignoring the curved length. I'm approximating it to be I'm taking it to be the vertical length, but in reality I have to take the curved length, but I'm ignoring that. Now, if we basically look at the two energies that are present in the problem, let's start by looking at the surface energy. And this surface energy is because of surface tension effects, and this would directly depend. If I just do a simple, going to do a simple scaling estimate, that would simply be minus gamma. Width is W is the width, and it would depend on the region which is the wetted portion of the surface, and this would simply be minus gamma W times L minus L dry. This would be the surface energy. And what about the elastic energy? Elastic energy would be EI times the elastic modulus is E. Give me a second here. W square by L dry cube. That's our elastic energy. So the idea of elastic energy is the elastic energy would be EI times the length scale L times the curvature term. This would be the square of it, the square of the curvature. The curvature in this case would be W by L. Now the L part that is of interest to us is basically the elastic energy from the top, because ultimately that is what is causing the bending. The forces on the upper surface is what is causing the bending. And if I have to be precise about it, I can write down these expressions exactly for a specific problem. For example, if I have to calculate this precisely, then this quantity would be, I'll write it in I have combined B and I, E and I into a quantity B. I have W square by L dry cube. So it's no more a scaling estimate. If you want the numbers to be precise, this is the value that comes out to be. And the other one, earlier one, which this quantity, if you have to be precise, I'll erase this part. The surface tension contribution will be exactly minus 2 gamma times L minus L dry. So we can write down the total energy. The total energy, we'll call it as E total, and this will simply be minus 2 gamma L minus L dry plus 3B W square by L dry cube. And if we minimize this with respect to the dry portion of this problem, L dry is the parameter. If we do this, then we see D by D L dry of E total will basically give us, meaning we are trying to minimize the energy with respect to the amount of dry region that is present as a parameter. And if we do this, we get 2 gamma plus 3b d square into minus 3 by L dry power 4. This quantity will be 0, and what we get is L dry power 4 will be something like 9 by 2. I'm using the word d, sorry, this will be w square. 9 by 2 w square times a parameter which is basically, we'll call it as LEC power 2. What is LEC? LEC is referred to as the elastocapillary length, and this quantity, elastocapillary length, will simply be B by gamma. That's the elastocapillary length. So I simply have L dry goes like W power half LEC power half. And it's important to note that this W, the dry portion of the liquid, is basically goes like the LEC power half, and it's basically, so surface tension is in the denominator. So let's basically look at how this works. I'm trying to hide an experiment that we've done. So the idea is that L dry goes like B power half and L dry goes like gamma power minus half. So if B increases, the sheets become more stiff and therefore they deform less, right? And L dry increases. And if you look at the figure, if L dry increases, the wet region decreases, right? So if you make the plates very stiff, then the fluid would actually fall. And the reverse is also true. If you basically make the plates very soft, then B decreases and L dry decreases, because as you can see, the scaling estimate that we have is that the dry portion of the liquid goes like B power half. Now the reverse is also true. It goes like 1 by gamma power half. So if you basically make surface tension very strong, then L dry decreases. L dry decreases means the length of the dry portion decreases, which means that the fluid is able to travel much further. So what this tells us is a combination of high surface tension and low B, that is the low bending stiffness, can promote fluid to rise much further than the case of two rigid plates. So in the case of two rigid plates, whatever is the height that the fluid has risen, now